So today I'm going to be going through an example of the TIPS technique, which we should apply to any problem-solving style questions, or specifically with the case of maths questions as well, to really talk through your thinking and to show that out loud rather than sitting in silence. It really helps to be able to demonstrate the steps that you're taking and doing that quite methodically. So this is a really good technique to demonstrate that. Now it comprises of four different aspects: tools, information, proposal, and state. And in this example question, you should all have this document, so you can read through this in your own time as well. But here I thought it would help to go through this with an example. So we're being asked here to sketch the graph of the function x cubed minus 4x over x cubed plus 1. And as it says here in the question, prepare to explain how you got the features of the plot. So that already is showing that we should be talking through our steps rather than trying to work it out in silence. So the first step is tools, and this means which tools do you have to your disposal that would help you to solve this. Now, the tools you should have developed hopefully at A level already, or IB, or whatever you're doing, and it's important to show that you can grasp these tools. So initially, as soon as you spot which tools, make it known. So here, firstly, we can find out where this curve crosses both of the axes. So for the y-axis, we set the whole expression equal to 0. And no, for the y-axis, we set the x values equal to 0. And we can find the y-axis intercept at 0, 0. And then for the x-axis, slightly more complicated, set the whole expression equal to 0. So here, this can only be true where the numerator is equal to 0, as we can't have a solution giving 0 from anything on the denominator. Perhaps infinity, but let's ignore that. So that would just simplify down to x cubed minus 4x equals 0. And from that, we can calculate these three x-axis intercepts. X-axis intercepts, including this 0, 0 that we found on the y-axis. So these are our three intercepts to look at. So that's perhaps the most simple tool that we have here. The next one would be figuring out how to find the slope of this function and how that might change depending on x. And for that, differentiation is key. Now, I'm hoping you've all come across differentiation before. And one of the many tools within differentiation is the quotient rule, which I won't go through here, exactly the steps, but it gives us this expression. You might want to refresh that if you haven't. Well, more generally, you should refresh the quotient rule and the product rule, and also the chain rule, as well as standard differentiation. These would be expected for this sort of question. So it's also very useful here. We have this expression from that for the gradient of this function, dy dx or f dash x. Fantastic. So the next stage is information. Now, what information are we given in this question? Not much. So, and there might be an example where there's more information in the question. But what we can work with here is the fact that this has a numerator and a denominator. This function will not be defined for when the denominator is equal to 0. And that will give, I hope you've seen this before, this will give a discontinuity at the value of x that gives a denominator equal to 0. And this exactly is where x cubed plus 1 is equal to 0. And that's only the case where x equals minus 1. Now, if there were more information in the question, it would be, you'd have more of a chance to talk about what you're given and talk that through. But here, that's really it. And this discontinuity makes the graph a little bit more complicated, but will help us to explain a result that we find next. So proposed. We should use the information that we've got to already and propose a way forward with this question. And what I would suggest is use these different intercepts that we've found and test their gradients. So we know the x value for each. We don't even need the y value for the intercepts. We just test these 3 x values. So when at the first one, well, at the second one here, minus 2, 0, we find a negative gradient of greater than 1 or less than minus 1. At the second one, we get a negative, at 0, 0, for moving along the number line, minus 2, 0, we get minus 4, which means it's steeper than the gradient at the minus 2 intercept. So we've somehow gone from a negative gradient at one intercept, one root, to an even steeper gradient at the next one. So, and the way to explain this would be, well, we know now that there's a discontinuity at minus 1. So this would explain how you can go from 2 negative gradients and also go back to a steeper one. We tend to assume usually that a graph like this would go back up to a positive gradient. And then at the final intercept, x equals 2, we get a positive gradient of less than 1. So that's summarized here. A negative gradient at the first intercept, a steeper negative gradient at the origin, and then a positive gradient at the third intercept. And this might seem a bit uncomfortable at this stage, but I think it's always best in the proposal stage to suggest an initial sketch or an initial answer to the question. You can come back and amend that and improve it, but it shows that you're already thinking about where this question is going. So we could propose this rough sketch. Here you can see the graph having a negative gradient, and then at the discontinuity being not defined, and then coming back down to the second intercept with a steeper gradient. You could have drawn that slightly better than I have there, but we see what I mean. And then returning back to a positive gradient. So that would help to explain A, the intercepts, and B, the gradients at these 3 intercepts, using the discontinuity from the question. Now, a final proposal to amend and improve what you've done already, you could consider the extremes. So what happens when we're all the way over on the left-hand side at minus infinity, and what happens when we get to positive infinity? How do we explain that? And what happens to the gradient at those points? So this is slightly dodgy maths, but you can see hopefully what this comes to. By plugging in minus infinity, we get to an expression with a numerator of 0, and the same for positive infinity. So furthest on the right and furthest on the left, we observe a 0 gradient. So rather than this sketch that I've drawn here, the curve is going to flatten out at both extremes, as I've stated there. And then the final step is to state and give a final sketch of what you are what you're asked to do. And given that we don't have a computer program or even much time to solve this, That's also something you can state. We don't have all of the tools to our disposal that would enable us to perfectly draw this graph. And that might include, indeed, where this turning point is down here. But what we've shown here is that you have the tools, the important tools, especially differentiation, to analyze how this relatively complex curve looks, and also to consider its intercepts as well. And you've considered this at the extremes. And that, without a calculator and without more advanced computer programming, would be a very good answer to this question. So just to repeat, we went through the tools that we have to our disposal, the information that we're given in this question. We propose a way forward, and we also can improve that proposal. And then finally, we state A, where we've come to, and B, how we could improve this if we had more time, more tools. So that would be my formula here with an example for a perfect TIPS technique.